Well, hello and welcome YouTube. Mr. Robbins back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and privilege to be serving you here today, as it is every day here in my virtual classroom. I am looking at integrated math 1 material with you guys involving segments, angles, segment addition postulate, angle addition postulate, distance formula, midpoints of segments, on graphs and not on graphs, transformations, reflections, rotations, translations. There's a question on dilations a little bit without using the word there. Bunch of things all packed within one, and a couple properties of equality within there. There's a PDF down in the description section below if you'd like to download it and take a look at all 20 questions that I'm going to cover here, which is review for my integrated Math 1 classes. Without further ado, guys, with the quick button press right here, let's go ahead and get started. Right here, number 1. Why is the midpoint of segment ST not shown? You know what? We're going to show it because we're going to draw this thing. If the length of SY is 7.2x, what is ST, the length of ST in terms of x? A drawing always helps you guys. When in doubt, draw it out. Or as my old student Kelly Wakasa says, do what excites. Co-fun. All right, here we go. Y is the midpoint of segment ST. If this is a segment, I can call ST like this. And Y is the midpoint. The midpoint literally divides the thing into two congruent parts, here and here. Now the thing says if SY is 7.2x. So SY is the length right here. This can be 7.2x. And it says what is the length of ST, the entire thing in terms of x. Well, here's the thing. If SY is 7.2x, then YT is also going to be 7.2x because y serves as a midpoint. Dividing this into two congruent parts, that means I can express both equivalently with the same values. Now I can use what's called the segment addition postulate to go ahead and add these two things up, 7.2x with 7.2x, to get the entire length of ST. Another way of me writing that is that the length of SY plus the length of YT equals the entire length that is ST. That is 7.2x times 2, or 7.2x plus 7.2x. That is going to give me 14.4x. When it says in terms of x, they're saying, we don't know what x is. I don't even know what x is. I couldn't tell you. They're saying have x in your answer, basically. That way, if they did tell you what x was, we could substitute it right into there, right there, and we'll be set up. All right, number 2, name the definition, postulate, or theorem used to justify your reasoning in number 1. Well, there were two things that I used, and like when I look at that, I'm trying to think of what the best version of that answer is. Definition, I'm using the definition of a midpoint for sure, because when they use the midpoint property, they're using midpoint right there to get me to know that this is 7.2x basically, or that I can double this. But also, I guess technically I did use the segment addition postulate there as well. The segment addition postulate. I don't know if that's something that's a requirement of sorts to use, because like I said, I could have doubled that amount as well. It's probably more about definition of midpoint for segments that I'm using there. So I don't know what the better answer is. I can't think of a theorem that I'm using in that one though. Definition of midpoint, segment addition postulate. Pretty good. All right. Numbers 3 and 4. Use the graph at the right. Name the new coordinates f prime, g prime, h prime, I prime if the figure is transformed from xy to negative x, comma, 1/2 y. Basically what happens is the original x coordinate remains the same x value except you take its opposite sign. And then, let's see. They don't ask you to graph it. I think I will graph this thing. And then take the original y value, the y coordinate there, and keep it the same except, take half of it. So let's go ahead and figure out what these new coordinates are after we do this. For every value, let's first look at the originals, okay? F was originally at negative 4, 4. I'm looking at the graph over here. It's at negative 4, 4. That's F. G was originally at negative 2, 0. H was at 2, negative 2. These are not the answers. These are the scriptures going into what I have to do work-wise. There's not a lot of room here, and I'm going to be doing a little bit of work. And I was at 4, 1. So what I'm going to do here, guys, for all these things, I'll show you with an example. I'm going to do them all, but I'm going to take the negative 4 on f, for example, that's x, and I'm going to take its opposite. It'll become the opposite of that value there. So let's actually mute these into blackness, and let's get these in blue as the actual ones. So f prime, I'll be taking the opposite of -4. I might not show all this work for the other ones. And I will be taking half of its y value being 4. Hopefully there's not too many parentheses there. So that becomes an f prime value of the opposite of -4 is +4, and half of 4 is 2. F prime exists at 4, 2. That's its value. That's its new value. So 4, 2 is right there. This is f prime. Okay. G prime, I'm going to be doing the same thing here. I'm going to take the opposite of the g value, the x value for g. So the opposite of -2 is +2. And then I got to take half of 0. Hey, that's still 0. So g prime is at 2, 0. I'm going to plot that right there. Call that g prime. H prime is at 2, 2. Let's see here. 2, sorry, I had a brain fart. I was thinking of something else in the back. Okay, H is at 2, -2. H prime, the opposite of 2 is -2. And then I take half of -2 and I get -1. So H prime is going to go over here. You know what I was thinking about? I was thinking that I didn't assign these first 4 problems to my students because I was thinking this was a dilation problem, and I'm thinking maybe I should have. And I made a mistake for that thing because it's still good practice for them. It's something that they did do. I thought this was a straight up dilation problem, and I jumped the gun. I prime, take the opposite of 4 and I get -4. And take the opposite of 1, not very fun, but I do get 1/2. Or I said the opposite of 1. Take half of 1 and you get 1/2. So I have -4, 1/2 right there. That's I prime. And again, I don't know if they asked you to graph this, so to speak, but let's go and take a look at this graph here. What happened was there kind of is a reflection. This thing did reflect over the y-axis. That's why it has the appearance of I being on the left side instead of the right, and all the other ones doing that. But then the y values got halved. And actually, that's not an example of a dilation, reduction, or enlargement because only the y values got halved. You can see that it shrunk this way, but it did not shrink this way. So that would be the drawing here. Now, is this a rigid motion? No, this is not a rigid motion because a rigid motion means that all corresponding parts need to remain congruent. They need to have the same measurements because corresponding parts, and by parts I mean sides, like side lengths, segments, and angles, corresponding parts do not have the same measurements. Things shrunk in this, specifically with regard to height, but everything else shrunk. The distance from F to I is actually a little bit longer than the distance from F prime to I prime, just because these are two closer values vertically, even though they're the same distance apart horizontally. All right, 1 second. Okay, here we go. Numbers 5 and 6. Now, this is where my students start on this stuff. Students of mine, go ahead and take a look at some of the top problems still. I still think this is stuff that is good for you to know. It's nothing I'm necessarily going to ask on your test, so to speak, but it's still some good to know material that can be still helpful for the over-encompassing problems that could exist on your test. I don't know how else to explain that, but still take a look at them. They're still beneficial. All right, use the grid below for 5 and 6. All right, number 5, draw the pre-image and image of a triangle with coordinates t, u, and v under a transformation rule from xy to x plus 1, y minus 3. So if you did see what I did in the last rule stuff, if you guys stuck around, you can kind of see how those things were applied. We're going to apply the same instances here with t, u, and v. Let's plot t, u, and v. T is at 2, 1. U is at 0, -1, and V is at 3, -3. These lines are laid on very thick on this graph. It's really hard to even with color on my thing, it's hard for you to really see where all those things are. But triangle T, U, V is right here. This triangle is about to undergo a translation, and it's a translation because these items just shift a unit to the right and 3 units downward. That is what that means, and if you are unaware of that, you can still apply the rule, which is what I'm going to do here. In fact, let me give it a different color for this. 1 right and 3 down. X increases by 1, they go 1 right, and Y goes 3 down. But let's do it based on the rule stuff here. T prime, what's going to happen, guys, is we're going to take 2, which is my X, and add 1 to it. 2 plus 1 is 3, and then 1 for Y, subtract 3 from that is -2. So T prime is going to be at 3, -2. So let's take a look at where that is. 3, -2 is right here. That's what we call T prime. You can see that that goes 1 right and 3 down from T. That's how that translation idea occurs. U prime goes from 0 on X to apparently 1 on X. 0 plus 1 is 1. And then -1 minus 3, that goes further negative. That's -4. Remember, we were at -1. Now we go down 3. That's at -4. So U prime is at 1, -4 right here. To confirm one more time, that is 1 right and 3 down of U. And then lastly, V prime, 3 plus 1 is 4, -3 minus 3 is -6. So we go at the very low end of this thing. That is 1 right and 3 down of here. That point is indeed for -6 for V prime. And let's connect those dots together, and we get another triangle. A little bit of overlap, but in a translation, the object does not reorient. Both of these triangles, this is a rigid motion, by the way. Both of these triangles here are equivalent in nature in every which way. It didn't even rotate or reflect at all. That being said, we are about to do a reflection here on number 6, but before I do that, just keep in mind one more time, if you understand what this rule is stating here, you don't have to calculate anything. If you have the graph, just go 1 right and 3 down on each of them, plot those points, and you're actually set. All right, number 6, on the grid, draw a reflection of triangle T prime, U prime, V prime across the y-axis. Label it triangle T double prime, U double prime, V double prime. Hang on a second. Okay. Hang on. Let me pause this recording for a second. I need to respond to this. Okay, sorry. Here I go. Number 6, are we on number 6? I think, okay. On the grid, draw a reflection of triangle T prime. Okay, so what we're going to do, guys, we're going to take this green one, or these points that are right here, if you will, and we are going to reflect them across the y-axis. Now, one of two ways you can do this, either by the graph or by the rule. They don't provide the rule for you, but in case you're curious on how to reflect across a y-axis, that rule would be going from xy to -xy. Very similar to the one that we saw actually back on number 3. The difference is we're not taking half of y when we do it, but it will reflect. If you notice, f reflected across the y-axis here to become f prime, but shrunk. We're not going to shrink these when they reflect here. We're going to get a drawing that ends up kind of looking like that, right? But because that's a reflection of the green one. So I'll do both. We'll take a look. We'll confirm that both of them do work. Let's start with the graph, though. That's probably what's expected of most people when they're looking at this one. So let's look at U prime to begin with. And we are doing the green triangle with the primes. That's what they're asking us to use. So here's the y-axis right here. U prime is only 1 unit away from the y-axis. And the reflection, we'll show it on the other side, also a unit away. This will be U double prime right there. 2 apostrophes, hopefully you can see that. T prime is 1, 2, 3 units away from the y-axis, and let's go 1, 2, 3 units on the other side. That gives us T double prime right there. And then V prime is 1, 2, 3, 4 units away, so 1, 2, 3, 4 units on the other side gives us V double prime right there. And that will be the graph. Those will be the points. So in connecting those dots, a little thick, laying on a little thick there. Let's get that. There we go. Right there, guys. So there's a reflection across the y-axis of those ones, and it didn't shrink like the other one did. That one's fine, set in stone. Now, if we applied this rule, would this make sense what happened here? Take the x values of these and make them negative. See if U double prime is indeed at -1, -4. Yep. And then T double prime at -3, -2, and V double prime at -4, -6. Yeah, that's where those things exist. You just take those x values and you change those signs, and that's where they go. So if you know that rule, if you're aware of that, you could, of course, always use that. Or just reflect across your axis if you know where it's drawn. All right, let's go ahead and move forward, guys. Number 7 through 9, a couple more transformations. And I know there's another transformation on the back. It's no more difficult than what you saw actually in number 5. It's just another version. But here we go. Number 7 through 9, use the figure to the right. Right here, it's a quadrilateral ABCD. Let's reflect ABCD across the y-axis. So we just did this last time. Let's go ahead and do it again. And if anything does make sense from last time, you just change the sign of the x's. So from D, that's negative 1, 5, becomes positive 1, 5 for D prime. Right there. This will be this guy. Now, you can also do this, guys. You don't have to reflect across point by point. Well, you do. But you can go in relation to the other points. So you know how C is a unit away from D to the left? When it reflects, C prime will be a unit away from D to the right. You know, because the reflection across the y-axis only changes the x. Now here, B was 3 left and 1 down of C. B prime is going to be 1, 2, 3 right and 1 down of C prime. Just another way to do it. Just showing it to you because some people might prefer this. It's a little more efficient if you know what you're doing with it. A is 3 down from B. A prime will be 3 down from B prime. And once again, only the left and right swapped, not the up and down when you reflect just across the y-axis there. Again, as that rule showed, just the x changed sign, not y. And in connecting these dots here, you're going to see that nice clean reflection right there. And hopefully you can see that across the y-axis. Boom. All right, now we're going to take A prime, B prime, C prime, D prime, and reflect it across the x-axis to A double prime, B double prime, C double prime, D double prime. So same-ish goes, only now here's the x-axis. We're going across this way. A prime is 1 unit away, so A double prime will also be 1 unit away. Remember, we are doing this from these ones, not these ones. Now, as I kind of did last time, I can do things in relation to the other points. If B prime is 3 units up from A prime, B double prime will be 3 units down from here. And the reason is because when we reflect over the x-axis, hopefully it's making sense, they're going distantly away this way. Now left and right stay intact. Up and down are the ones that flip. So in relation to that, C prime is 3 left and 1 up. C double prime will be 1, 2, 3 left and 1 down. That becomes C double prime right there. And then D prime is just 1 left as C prime. D double prime is 1 left just as C double prime is also 1 left. And connecting those dots there. And again, you can go based on the rules, guys. You can go based on the just counting across the axes and such. There's no fault in that. No problem. I'm just trying to give you another little speedster approach that does work. All right, so that was this guy here. You can kind of check these off. Check, check, all done and done. Or, of course, if you use some math to do the rules, you can write those points down. All right, what type of rotation is ABCD to A double prime, B double prime, C double prime, D double prime? We're going from this original shape right here into this one. And yes, guys, believe it or not, this actually is a rotation. I don't know if you can tell here. If I take this object and I actually rotate it 90 degrees, that almost looks like this. It's a little different because a rotation of 90 isn't the same as a reflection across an axis, but we did 2 reflections. And if I do another rotation right here, I get this. Take a look at how that's supposed to match up there, guys. But this is a 180 degree rotation of this thing around there. I want you to think about that in some other terms. I'm going to use my hand as an example of this, guys. If I take my hand right here, okay, so look at where it is right now, and I'm going to reflect it across this axis right here. I flip it over, that's what I'll get as a result. Now if I flip it across this axis, that's what I'll get as a result. Well, what's this equivalent to from the original? Here's my original. Here was my ending. You guys see that? That's a 180 degree rotation there, despite the fact that I did 2 flips. Have you ever looked into a mirror and you were normal again? That's what's happening here. The difference is these mirrors are perpendicular to each other, so you're probably looking at another version of you that's now upside down, just because of the nature of, you know, if I looked down at a mirror that's looking back up at me, then that guy's upside down, right? And then if he looks into a mirror, now he's a normal version of me. So that's what's happening there, guys. 2 flips. I did an equivalent in one of my lecture videos of old. New for my students because of when I posted it for them. But if I take the letter F, guys, and I go ahead and I do a reflection, let's go ahead and flip it left to right. So I'm going to go ahead and flip it this way. right? There's one reflection of it. Now let's take that backwards f, that backwards f, and let's flip it over upside down. And you see what's there. Well, what's that f equivalent to right here? I could just take this first f and rotate it. It's not going to be in the same spot, but rotate it like that. See how it went upside down? So what's the answer to this? What type of rotation is this? This is called a 180-degree rotation. It's 180-degree rotation. Now, should it matter that it's clockwise versus counterclockwise? Not really, because 180 degrees clockwise or counterclockwise is the same thing. You end up in the same spot. I don't know if there's a technically it should be clockwise kind of thing, but if we did kind of go in this direction, so maybe technically it kind of is clockwise. But since it is, once again, 180 degrees, whether you say one way or the other, it's not going to matter. You're in the same spot. There's number 9. All right, number 10. And 11 and 12, by the way, I'll just take a sneak peek at those drawings, guys. Numbers 11 and 12 right here also have angles. So I'm going to be drawing something on number 10 to kind of assist you with it. Let's take a look at that. Number 10, ray SV is an angle bisector of angle RST. If the measure of angle RSV is 7x minus 34 degrees and the measure of angle RST is 10x minus 2 degrees, find x, show all work. Just to go back really fast, guys, remember when I said on number 1 was it really helped to draw this thing out? I hope you agree that it did. It really did help to draw this thing out. So if I go to this one right here, it would help to draw this thing out just as the other ones have drawings. I have some angle RST. That means that I have a vertex S, and split apart from that vertex S, I have a point on this arm called R and a point on this arm called T. It doesn't matter really how you draw it. Don't make it too small like that, because we're going to go right in the middle of this thing with an angle bisector known as ray SV. Here's that point S, and here is a V that's coming out from there like that. Now, the important term here is angle bisector, and if this wasn't given to us, then we actually couldn't solve this problem. What an angle bisector does, it's not just something that sticks out that splits the angle. It splits the angle into 2 equal parts, such that this and this are not only congruent to each other, they are equal angles, but also each of these are exactly half the measure of the entire thing. It's exactly half of it. So now they say if the measure of angle RSV is 7x minus 34 degrees, that's this guy right here. 7x minus 34 degrees is for just this angle right here, guys. That's half of the overall bigger RST, right? And by the way, they give us the measure of angle RST. The entire thing, they call that 10x minus 2 degrees. So that's this whole thing right here. Not congruent to those two. I'm just giving an arc mark to label. This is going to be called 10x minus 2 degrees right there. And they're saying find x, show all work. So this one actually serves so much like the midpoint one you saw in number 1. On number 1 here, this is for my students who probably didn't see number 1 because I told you to skip it, but now I kind of feel like you should take a look. This is an example of one of those things where, like, feature-wise, this kind of does make sense for number 10. So on number 1 here, if you take a look, 7.2x was all that we knew right here, but we knew that this was a midpoint, which means it divided into 2 equal parts. So even though I wasn't told this was 7.2x, I could plug it in. I could say this was because this was exactly half and was equal to this, and I could fill it out. So on number 10, we can do the same kind of thing. They didn't tell us what the measure of angle VST was right here. They never told us, but they did tell us that SV was an angle bisector, which means these are broken up into 2 equal parts. So if this is 7x minus 34, we can absolutely express this as 7x minus 34 as well, because they're equal, because of the angle bisector. You can't just assume otherwise. They tell us that information that's useful for this. So both of these are like 7x minus 34s. And furthermore, now we can create an equation for all this stuff involved here that says if I add these 2 angles up, because they're adjacent to one another, they're only split by this, but if I join these 2 things up right here, it will equal the entire angle measure. So if I take that 7x minus 34, that's from measure of angle RSV, plus the 7x minus 34, that's the measure of angle VST, that will equal all of this expression for the angle, which is 10x minus 2, like that. And that's a setup for an equation to solve for x, and the rest is algebra. Now, an alternative way to do this is the same thing, but an alternative way to do this is if you didn't yet write the 7x minus 34 here, you know that this is half of the entire angle. So how do you make the entire, how do you make them comparable, make them equal, you would have to double this. So you would say 2 times 7x minus 34 equals 10x minus 2. They're both equivalent. Doubling this is the same as adding it to itself. So I'm just kind of giving you that mindset that either or is totally fine, guys. It's not going to matter. I'm just going to go ahead with the top one because I got to combine like terms. 7x plus 7x, y'all, is 14x. Negative 34 plus negative 34 actually goes to negative 68. And I got that brewing right there. Subtract 10x from both sides and add 68 to both sides. I get 4x equals 66. Divide both sides by 4. This is actually a decimal. I'm going to start off with the fraction version. This is 66 over 4. I like whenever, I don't know if I really do, but I like whenever my students would get an answer like this and like, Mr. Robinson, there's no solution. Mr. Robinson, there's something wrong with the answer. Mr. Robinson, did I do it right? Yeah, it's okay. Divide top and bottom by 2. We get 33 over 2. That's my favorite answer. But as a decimal, if it was like a contextual word problem, that is 16.5. Also very valid. You can put them up right there. That says 12. That should be a 10 right there. So number 10, 33 halves or 16.5 units. Oh, degrees. No, it's just units. It's not a length actually. These go into here. If they asked us to find the measure of an angle, we could plug that in for x as well. I was thinking I was on a segment problem there for a second. All right, let's go to the back page, guys. Halfway through. All right. Number 11. Find the measure of angle IJA if the measure of angle AJK is 61 degrees. That is, AJK is this one right here. That's 61 degrees. Thank you for the drawing. I'm going to label that out. And the measure of angle IJK, that's the whole thing, is 153 degrees. Show all work. So we know that the whole thing is 153. We know this little part is 61, and we're trying to find this missing guy right here, IJK. So like the last problem I just did, guys, it's a matter of addition. If I add this 61 with this unknown, I should get 153. Now, I know the majority of my students are going to say, just subtract, and you're not wrong. Subtraction does work. I'm going to set this up algebraically in a way that might help me for a problem beyond that, number 12, wink, wink. So to set this one up to start with, guys, I'm just going to use the concept of what's called the angle addition postulate. I want to give you the full bore version to start off with. The measure of angle AJK is that little guy, and then the measure of angle IJA is that little guy right there, and those added together equal the whole thing, the measure of angle IJK. That is the angle addition postulate in full form. I'm going to do substitution with the values that I do know. The measure of angle AJK is 61 degrees. Measure of angle IJA is unknown. That's a variable. This is like an x. It's a variable. Measure of angle IJK is 153 degrees. From that setup, as we saw for measure of angle IJA, you subtract 61 from both sides. That's where the subtraction occurs. And that, to me, is my favorite preferred setup work-wise when I see something like that. It's complete. It lets me show the angle addition postulate. It's addition, right? I'm subtracting algebraically to solve for it, but this is addition to start off with. Anyway, 153 minus 61 is, I think, 92. So that's going to get us 92 degrees right there. That is your final answer for the measure of angle IJA. Let's place it in purple because that's what we had for the arc there. All right, let's go on to number 12. Very, very similar. The difference is now we have algebraic expressions instead of straight up numbers. Well, 42 is a straight up number. Let's look at that. Measure of angle ABK is 42 degrees. ABK is right there. I really like using these drawings whenever I can, but you might have noticed, guys, I didn't actually need this drawing to set up angle addition postulate, although honestly, it kind of helped because it lets me kind of know what's what, what's the big angle, what's where, and whatever. These two added up to that. But to me, in the end, it was a substitution. This is 61 and this plugged in. Know what I mean? So we can do the same thing over here, but I got a 42 for that. KBC is 12x minus 4. I'm just going to use all blue this time. 12x minus 4 for that small guy. Not small, but... And then the big whole angle thing for ABC, they tell us is 17x plus 8. One more time, guys. Angle addition postulate. Adding this with this to get whole thing. Now, we're doing more than just finding the measure of some unknown angle. Well, we are doing that. We got to find x first, and then we got to substitute that in to solve in the end. So here we go. We have 42, the measure of angle ABK, plus 12x minus 4, the measure of angle KBC, equals 17x plus 8, the measure of angle ABC. Notice these weren't told to be angle bisectors. It's not dividing into two equal parts, but we are just adding those parts together. We have enough info to help ourselves. Combine like terms, guys. 42 minus 4, that is 38. So 12x plus 38 equals 17x plus 8. Hope there are no decimals on this one. Subtract 12x from both sides, I get 5x. Subtract 8 from both sides, I get 30. And then divide both sides by 5, we do get x equals 6. Now that's great, but that's not what we needed. This helped. It's not the answer yet. We got to find the measure of angle ABC right here. Now we have an expression for measure of angle ABC, which is 17x plus 8. So what we're going to do, guys, is we're going to take the 6 that we got for x, substitute it in, and then determine that number. 17 times 6, 42 plus 60 is 102. So 102 plus 8 is 110. So the measure of angle ABC, I really want to move this stuff over now. The measure of angle ABC is 110 degrees. There you go. And you can watch ABC on Channel 10. Okay, let's move forward. Number 13. In the figure below, the length of NL is 2x plus 5. Oh, you know I like my labels in my drawings. And the length of LK is 3x minus 18. Good to go there. And NK, the entire thing here, is 32 units in length. Find LK, show all work. Very similar to number 12, guys, only now instead of angles we have segments. Arguably the easier one to kind of look at. We'll use the segment addition postulate, which states when we add these two things together, this plus this, it's going to equal the entire thing. We'll solve for x and of course use that x then to substitute and find LK. So we're going to have 2x plus 5 plus 3x minus 18. That equals 32. Combining like terms, I get 2x plus 3x, that becomes 5x. 5 minus 18, that's minus 13. Add 13 to both sides, we get 5x equals 45. Divide both sides by 5, we get x equals 9. Still need to solve for the length of LK right here, given that we know that that is 3x minus 18. So we're going to take that 9 and substitute it for x. 3 times 9 minus 18 is 27 minus 18, which I think is 9. 27 minus 18, which is 9. So I'm going to write LK equals 9. That is the length of just that guy right there. Hey, x was 9 as well. Little false positive there. If you got 9 as an answer and put that in just because you solve for x, well, you lucked out because you had a little more to do, but we still get LK is 9. Excuse me. Okay, numbers 14 and 15, I can almost run in conjunction with one another. You'll see how I do it in a couple forms here. But I have the segment AB. They say use the coordinates in number 14, so they are in conjunction, but we're going to do two different things. Number 14, segment AB has endpoints A of 4, negative 4, and B, this should say B here, negative 6, comma 4. Find the midpoint of segment AB, show all work. Well, finding the midpoint is as simple as averaging the two x values that you have in this set and the two y values that you have, and that coordinate pair, that ordered pair there, guys, will be your midpoint straight up. If I treat A as having my x1, y1 values and B as having my x2, y2 values, then I can substitute into this formula and go to work. So my midpoint for this guy here, I'm going to take x1 plus x2. I'm going to add 4 with negative 6 and then divide that by 2 and thereby averaging them. When you average two numbers, you do get its halfway in between number, also known as midpoint, mid value. And then negative 4 plus 4 divided by 2 for the y values there. Kind of short on room here, huh? Midpoint right there. That'll be 4 plus negative 6. 4 minus 6, that's negative 2 over 2. Negative 4 plus 4 is 0. So that's 0 over 2. And that will give us, actually, let's put it right down here. That'll give us a midpoint of, negative 2 over 2 is negative 1, and 0 over 2 is 0. So the midpoint is negative 1, comma 0. I'll show you another way to do it in a graphing form. It's not going to be fantastic, but it will run, like I said, in conjunction with number 15 when I'm done with number 15. Number 15, use the coordinates in number 14, these two right here. And I'm going to actually use the x1, y1 stuff right here too. To find the length of AB, segment AB, show all work? We'll use the distance formula, or at least that's what they're telling me to do that. How dare they? The distance formula is taking the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. I'm not a big fan of the formula itself because of the... I'm not going to talk about it. It's fine. There are other conventional ways, and those who forget to memorize and stuff, my students will be able to use this just straight up on the test, so that's cool. All right, so D equals square root of... I have negative 6 is my x2, so negative 6 minus my x1 is 4, so that's squared, plus, HEI, 4 minus, now this is a negative 4, 4 minus negative 4 quantity squared right there, right, the y2 minus y1, you don't just put 4 minus 4, that's subtracting a negative 4 there. All right, let's keep going here. Negative 6 minus 4, guys, is negative 10. We're going to square that number. Be careful when it comes to using a calculator. I'll explain why in a second. 4 minus negative 4, that's the same as 4 plus 4, guys. That's going to be 8. So we square 8 right there. Be careful using a calculator, because if you type negative 10 squared in your calculator, you might have it say negative 100. And that's because you might have forgotten to use parentheses around that thing. If a calculator sees parentheses around the negative 10 and squares it, you'll get your proper number of positive 100. But if you don't, and you ignore it outright, it might give you negative 100. You might just trust that answer. Squaring a negative number should give you a positive result, and that's what we're expecting to get here. So we're going to get the square root of 100 plus 64. So that becomes the square root of 164, which is an irrational answer. If you are in a group, not my students, but if you're in a group that's simplifying radicals, guys, we can definitely divide it by 4, 4 and 41. So this would simplify to 2 root 41. I'm good with my students just leaving it like this. If you approximated it, I don't actually know. I don't have the calculator on hand right now. Oh, my phone. If you approximate it, it's somewhere between, it's closer to 13. It's probably around 12.8 something. 12.8, 12.9-ish. Let's see. Probably closer to 12.8. 164 square root. 12.80. I'll just write 12.806. So square root of 164, which is approximately 12.806, just to get you kind of a value within there. But square root of this is a perfect number. That's approximated. This is also a perfect number. My students are not rationalizing right now. They're not simplifying. Excuse me. They're not simplifying the radicals. All right, I got just a few more questions left. These will actually go kind of quickly. Number 16, if triangle ABC is the pre-image, right here, show the image A prime, B prime, C prime, if it transforms by the rule xy to x minus 5 and y minus 1. Let's try this one specifically just with the, I know there's a rule in place here, but if you remember last time, guys, we can apply the rule in such a way that we don't have to mathematically write out the vertices if you know that this means left 5 and down 1. Because the subtractions, it's left for x and down for y. There's a vector here. The original problem says follow the vector, and that's what the vector's doing. It's going left 5 and down 1. And we're going to apply that vector for every one of these points here. So A prime will be left 1, 2, 3, 4, 5, and down 1. And there we have A prime. This is, again, another translation. Unfortunately, guys, no rotations on this one. There are some other videos that I'm sure I can find for you that do apply rotations. At least from my lecture videos, there definitely would be some. But yeah, no, there was only identifying a single rotation on this one. Although this thing is review for my students here, they are well aware of the fact that there are more things that they got to review based on the things that we learned. This is just but a little bit of what we haven't seen for a while. We sure haven't seen the distance formula for a while, so I think that was big for them. Anyway, there's the drawing, guys. You could have also found all the points and then subtracted 5 and subtracted 1 and such, but I think that also applies just as well. And if you know what that means, you're golden. All right, number 17, state the hypothesis and conclusion of the statement. If a plane contains 2 lines, by the way, my students are cut off after this problem, after 16. They're done. So, because this stuff is stuff we'll kind of learn a different day. If a plane consists 2 lines, then they are coplanar. Now, I'm not going to really talk about what all this stuff actually means right now, but just the hypothesis and conclusion. This is beyond math. This is just kind of English. This is like linguistics. This is sentence structure. There's an if here. If is something called a hypothetical. They're saying, I don't know if this is true or not, but let's say that it were true. Let's say hypothetically that it were true. That makes this thing a hypothesis. Hypothesis says if a plane consists two lines. So the hypothesis is that a plane consists two lines. And again, if you don't know what that means, right now, unfortunately, just for my student sake and such, I'm not really going over that. I could give you a drawing of it, but so if you know what those things are, that'd be great. So here I have a plane. If I have a line here and a line right here, okay, on the plane. There we go. Conclusion. The conclusion is a then, assuming, right? If means assuming it's true, then we can draw a conclusion. Their conclusion is off the word then here, and the conclusion is they are coplanar. So the conclusion is those lines, I'm going to say those lines are coplanar. You could say they, that's fine. I just want to make sure that we know what the they is. Not playing the pronoun game with you guys. Those lines, yes, two lines that are on the same plane are indeed coplanar. Excuse me, a plane that consists of two lines would also be coplanar lines. That's all there is on that one. Okay, number 18. This will be a good one for my students, but I think we're saving it for our next unit and module. Angle ABC and CBD are a linear pair. Now, this will be important to draw to make sense of where the heck these things coexist. And then we'll kind of fill out this stuff here. So a linear pair means that we have a line divided into two adjacent angles here in such a way that, I mean, they are adjacent, but in such a way to represent that they are indeed supplementary, that they add to 180 degrees. If they call us ABC and CBD, notice that B and C are shared as letters here. So that means A is starting off as one of these, and it has to hit B going into it. So that makes sense that this is ABC. We can call this one CBD, like that. That's going to work out. It's a linear pair, guys. These are going to add to 180 degrees with whatever we do here. All right, angle ABC, its measure, oh, it's equal to CBD. Let's take a look at that. If they're equal, then I can make a drawing even better and say, hey, let's divide it up like that. Basically, this is an angle bisector, right? These are both 6x plus 6. 6x plus 6 here, 6x plus 6 here, both the same thing. It says find x. Now, the last thing that you want to remember, guys, is because it's a linear pair, this is a straight angle, semicircle basically, adds to 180 degrees. So if I add these two up, or heck, if I double it up, if I double the 6x plus 6's, I'm getting 180 degrees. There's your setup. Let's go ahead and solve for x. You could distribute the two. I'm gonna have a little fun with this, guys, just because it's something else you can do. I can divide both sides by 2 as well. If 2 multiplies to this thing, let's divide the 2 out. Let's make this number smaller. 180 divided by 2 is 90. 6x plus 6 is 90. Subtract the 6 from both sides right there. I'll get 6x is 84. And divide by 6, I get x equals, that's a clean number, right? 14. I get x equals 14. And I think that's all they want. Yes, find x. We're all good. X equals 14. I am done. All right. Numbers 19 to 20 state the property of equality used in each statement right here. Number 19 says that 7x plus 2 equals 51, then 7x equals 49. How did we get from this part of the equation here to this part of the equation here? That's kind of what's being asked here. Well, what happened is we subtracted 2 from both sides, right? And we do it from both sides to keep balance in this thing. This is otherwise known as the subtraction property of equality. That's what that thing's called right there. When you do the same thing to both sides, it's of equality, and that's what maintains balance. Also called SPOE. All right, that's 19. That's it. Number 20, if 5x equals 40 and 40 equals 3x minus 2, then 5x equals 3x minus 2. I'm going to rewrite those one more time. 5x equals 40, 40 equals 3x minus 2. By the way, that's a hypothesis. If this, then that, right? Hypothesis conclusion. Then 5x equals 3x minus 2. Well, what's occurring there, guys? Take a look at that. 40 is a shared expression here that is equivalent to both 5x and 3x minus 2. What basically happens is it looks like 5x kind of takes 40's place here. 5x is 40, right? It's the same thing. So what's it going to do? It's it's going to take 40's place right there. It's going to substitute in. I don't want to use the word substitution though. It's essentially substitution, but there's also another phrase that they use here because this is a full expression it's replacing. It's not just plugging in for x. It's not just one part of it. It's replacing the entire expression, the entire side of the equation. This is something called the transitive property. So 5x equals 3x minus 2 like that. So this is what's called the transitive property of equality. And the transitive property of equality states basically what you saw right here. It says if, and I'm running out of time, sorry, if A equals B and B equals C, then A equals C, as far as replacing an entire expression on one side of an equation like that. It's a substitution, but kind of a broader kind of sense of it. All right, that'll be it, guys. That is all of 1 through 20. Again, check the description section down below if you want to download this PDF, and there should be timestamps for each problem corresponding with all the bits there. Thank you so much, guys. Happy mathing.